November 14, 1940. Experimental bridging establishment, Christchurch, Dorset. The pencil moved with practiced precision as Donald Coleman Bailey sketched on the back of an envelope, his design rejected 4 years earlier, now suddenly relevant in ways that would determine the fate of nations. Outside his window, rain pelted the converted Victorian barracks, while inside, a 39-year-old civil servant worked alone in his office, officially on his own time, designing what his superiors had explicitly told him not to pursue during work hours. The bridge he sketched would have to carry 40 tons. The new Churchill tanks weighed that much, and the existing military bridges could barely support 26 tons. Every other engineer said it was impossible with the materials available. Bailey drew another line, completing a simple rectangular panel, 10 feet by 5 feet, that could theoretically do the impossible. What Donald Bailey didn't know, hunched over his envelope in that poorly heated office, was that his design, dismissed as too simple, too basic, too unlike proper military engineering, would carry more military traffic than every other bridge design in history combined. Within 4 years, his bridge would transport over 1 million vehicles across rivers, canyons, and demolished infrastructure from Tunisia to Burma, from Sicily to the Rhine. Field Marshal Montgomery would declare it responsible for shortening the war by months. General Eisenhower would rank it alongside radar and the heavy bomber as the 3 most important technical developments that won the war. But on that November evening, Bailey was just a civil servant who liked to tinker with model bridges as a hobby, working after hours because the War Office had told him to pursue his idea on his own time if he insisted on pursuing it at all. The collapse of confidence in British military bridging had begun 6 months earlier, in May 1940, during the retreat to Dunkirk. Captain William Spencer of the Royal Engineers watched his unit abandon their entire stock of pontoon bridges on the road to the coast. The bridges, based on designs from the Great War, required dozens of vehicles to transport, hours to assemble, and cranes to position. They were, Spencer would later write in his official report, entirely unsuitable for modern mobile warfare. The German blitzkrieg had moved faster than British engineers could build bridges. Tanks that needed to cross rivers to escape encirclement were abandoned because the bridges to carry them didn't exist or couldn't be built in time. Among the equipment left behind at Dunkirk were 23 complete sets of the Inglis Bridge, the British Army's most advanced military bridge. Each set cost £12,000 sterling, equivalent to the price of 4 Spitfire fighters. Lieutenant Colonel Charles Jarrett Kerr, who would later become one of Bailey's key collaborators, documented the loss. "We abandoned in France enough bridging equipment to span the Thames 20 times over, and we couldn't build a single bridge fast enough to matter when it counted." The crisis deepened through the summer of 1940. The new infantry tanks being rushed into production presented a problem that existing bridge designs simply couldn't solve. The Matilda II weighed 25 tons. The Valentine, entering production, weighed 16 tons, but concentrated that weight on narrow tracks that created higher pressure per square inch than heavier vehicles. Most devastating to existing calculations, the Churchill tank, still in development, would weigh at least 39 tons, with plans for versions exceeding 40 tons. Major Ralph Freeman Jr., posted to the experimental bridging establishment and son of the designer of Sydney Harbour Bridge, calculated that no existing military bridge could safely carry the Churchill. "We are," he wrote in a memorandum dated August 3, 1940, "in the absurd position of building tanks our own bridges cannot carry." The experimental bridging establishment occupied a collection of Victorian buildings and modern workshops on the outskirts of Christchurch, where the River Stour met the English Channel. Created in 1925 from the remnants of the Royal Engineers Bridging School, it employed fewer than 50 people, most of them civilians. The annual budget for 1940 was £17,000, less than the cost of 2 Inglis bridge sets. Here, in what one general dismissively called that collection of sheds and dreamers, the future of Allied military engineering would be determined. Donald Bailey had joined the establishment in 1928 after graduating from Sheffield University with an engineering degree in 1923. Born September 15, 1901, in Rotherham, Yorkshire, Bailey was a quiet man who rarely spoke in meetings and never raised his voice. He had spent 12 years designing incremental improvements to existing bridge designs. His personnel file reveals a methodical engineer who submitted 43 different proposals for bridge improvements between 1928 and 1936, of which 3 were accepted for minor implementation. The 1936 rejection still rankled Bailey 4 years later. He had proposed a modular bridge system based on lightweight panels that could be assembled like an enormous piece of military meccano. Each panel would be a welded steel lattice, 10 feet long and 5 feet high, weighing no more than 600 pounds. 6 men could carry one panel. The panels would connect with simple pins, requiring no special tools, no welding, no bolts beyond the initial assembly pins. The bridge could be strengthened by adding more panels side by side or stacking them vertically, adapting to any weight requirement. The War Office Evaluation Board had dismissed it in 3 paragraphs. Mr. Bailey's proposal lacks the engineering sophistication expected of military bridging. The simplicity he advocates as an advantage appears to be merely an absence of proper design. The pin-joint system is mechanically crude. The appearance is aesthetically unpleasing, not recommended for further development. 4 years later, with France fallen and invasion threatening, the general's definition of proper had changed dramatically. The catalyst for reconsideration came from an unexpected source. On November 12, 1940, Bailey attended a meeting about the failed trials of the Inglis Mark III bridge, the latest attempt to strengthen the existing design to carry 30-ton loads. The trials, conducted at the Christchurch testing grounds, had been catastrophic. The bridge had collapsed under a loaded test vehicle, nearly killing the driver. During the return train journey from these failed trials, Bailey found himself sharing a compartment with 3 senior officers: Major Stewart, Superintendent of the Experimental Bridging Establishment, Colonel Fowle of the Royal Engineer and Signal Board, and another senior engineer. They discussed the crisis facing military bridging with the desperation of men who knew that invasion could come within months. "The Hamilton design won't work," Stewart was saying, referring to another bridge design being considered. "Archibald Hamilton's design needs special equipment we don't have and can't manufacture quickly enough. Martel's box girder is strong enough," Fowle added, "but it's too heavy. We'd need specialized vehicles just to transport it." Bailey pulled out an envelope from his jacket pocket, a letter from his wife about household matters. On the back he began sketching, not speaking, just drawing. The simple rectangular panel, the pin joints, the way panels could combine. After 10 minutes he slid the envelope across to Stewart. "What's this?" Stewart asked. "The bridge I proposed in 36, Bailey said quietly. "But look at the weight calculations now." Bailey had spent 4 years refining the mathematics in his spare time. Each panel, constructed with standard steel angles readily available from any steel supplier, would weigh 570 pounds. But the crucial innovation was in how they combined. 2 panels side by side created a bridge that was not twice as strong, but 2¼ times as strong due to the load distribution. Stack them vertically, and the strength increased exponentially, while the weight increased linearly. 6 men can carry each panel, Bailey continued. No panel weighs more than 1/3 of a ton. Standard 3-ton trucks can transport them. Any engineering firm in Britain can make them because they only require standard steel sections and simple welding. No special alloys, no precision machining except for the pins. Fowle studied the sketch. How quickly could it be assembled? A 40-ton, 120-foot span? Bailey calculated on the margin. 40 men, 8 hours, less if they're experienced. "Impossible," Stewart said, but he was looking at the calculations, not dismissing them. "Let me build a prototype," Bailey said. "Give me 3 months." The room went silent. Finally, Stewart spoke. "The Minister wants solutions by May. If you're wrong, Donald, we'll have wasted resources we can't spare." "If I'm right," Bailey replied, "we'll have a bridge that can be manufactured by hundreds of firms simultaneously, assembled by ordinary soldiers, and strong enough to carry anything we can build." On February 14, 1941, Bailey received official authorization to proceed. The letter from the Ministry of Supply was typically bureaucratic. "You are authorized to develop a prototype of your modular panel bridge system for trials no later than May 1, 1941. Budget allocation, £2,000. The design team Bailey assembled in those first weeks was eclectic. Captain Charles Jarrett Kerr, a territorial army officer who was a structural engineer in civilian life, became his primary calculator. It was Jarrett Kerr who suggested the distinctive K-bracing configuration that would become the Bailey Bridge's signature. Ralph Freeman Jr. brought in valuable experience in stress analysis. Herbert Taylor, a welder from Birmingham who had been conscripted into the establishment, provided practical manufacturing insight that would prove crucial. The first challenge was the steel. Britain in early 1941 was desperately short of everything, especially specialized steel. Bailey's design deliberately used only standard angles and plates, the type every small engineering firm kept in stock. Bailey approached Braithwaite and Company, a West Bromwich firm that manufactured railway wagons. They had stockpiles of steel allocated for civilian contracts that had been cancelled due to the war. "You want to build a bridge from railway wagons steel?" Thomas Braithwaite, the company's director, asked when Bailey presented his proposal. "I want to build a bridge from whatever steel Britain has," Bailey replied. "Your steel, shipyard steel, any steel that meets basic specifications. That's the point." The first panel was completed on March 18, 1941. It looked, as one observer noted, like a piece of giant garden fencing. 5 feet 1 inch high, 10 feet long, a simple Warren Truss design with diagonal bracing. The welding was deliberately basic, something any competent welder could replicate. The pinholes were drilled to tolerances that any machine shop could achieve. Herbert Taylor lifted one end of the panel. 570 pounds, he announced after checking the scale. "I've carried heavier pub signs." The real innovation became apparent when they assembled multiple panels. The pin system Bailey had designed allowed panels to be connected in minutes. No precise alignment needed, no special tools, just sledgehammers to drive the pins home. The transoms connected the panels laterally, the stringers would carry the deck, and the entire system could be assembled by soldiers with minimal training. On April 2, 1941, they conducted the first load test. A single panel, supported at both ends, with sandbags piled in the centre. The calculations said it should hold 2 tons before failing. It held 2.5 before the first signs of stress. 2 panels bolted side by side held not 5 tons, as simple addition would suggest, but 7 tons, exactly as Bailey's distribution equations predicted. "It's the triangulation," Jarrett Kerr explained to the gathered observers. "Each additional panel doesn't just add strength, it redistributes the load across all panels. But the true test would come with a full-scale bridge. The prototype had to span 120 feet and carry 40 tons, the weight of a fully loaded Churchill tank. They had 4 weeks to build it. The construction site was a field adjacent to the River Stour, chosen because the ground conditions were poor, approximating battlefield conditions. Bailey's solution for assembly was ingenious in its practicality. The bridge would be assembled on rollers on one bank and pushed across the gap. A launching nose of lighter panels would be attached to the front, angled upward to compensate for the droop as the bridge cantilevered across the gap. On April 28, 1941, 3 days before the deadline, they began the final assembly. 40 men from the Royal Engineers, none of whom had seen the bridge before that morning, were given a 2-hour training session. Bailey deliberately stayed away from the actual construction, wanting to prove that the bridge could be built without expert supervision. Lance Corporal William Davies, one of the engineers, kept a diary that survived the war. "The civvy engineer showed us these panels that looked like fence sections. Said we were going to build a bridge to carry tanks. We thought he was having us on, but the bloody things went together like a child's toy. Tab A into slot B, bang in a pin, move to the next one. By lunch, we could see it was actually going to be a bridge." The pushing operation began at 2 in the afternoon. The bridge, assembled on rollers, had to be pushed out over the gap by manual labour. No cranes, no heavy equipment, just 40 men with push bars. As the bridge extended over the gap, the cantilever stress increased exponentially. If Bailey's calculations were wrong, the bridge would fold like a closing book and crash into the river. At 60 feet out, the bridge had dropped 4 feet at the tip, exactly as predicted. At 90 feet, it was down 8 feet, but still within calculations. At 110 feet, the launching nose touched the far bank. The bridge was across. May 1st, 1941, 9 in the morning. The testing team had faced an unusual problem, finding something heavy enough to test the bridge properly. They had never tested anything designed to carry 40 tons. The solution was ingenious. They used a World War I Mark V tank that weighed 29 tons, then loaded it with pig iron and additional steel plates until the total weight reached 40 tons. The tank began to move. The bridge deflected immediately, dropping 6 inches as the tracks reached the first panel. At the quarter point, the deflection was 18 inches. Still within parameters, but the sound of straining steel was audible. Halfway across, the bridge was deflected 2 feet. The driver later reported that he could feel the bridge moving beneath the tank, like driving on a living thing. But it held. The panels distributed the load exactly as Bailey had calculated. When the tank reached the far bank and drove onto solid ground, there was silence. Then Stewart spoke. "Do it again." They ran the tank across 14 times that day, forward and backward, fast and slow. They stopped it in the middle and left it there for an hour. After the 14th crossing, they inspected every weld, every pin, every connection. Minor wear, no structural damage. General Charles Macready, representing the General Staff, had watched the entire demonstration without comment. Finally, he approached Bailey. "How many of these can you build?" "Me?" "None," Bailey replied. "But Britain?" "As many as you need. Any engineering firm can make the panels. Any soldier can assemble them." "How many firms?" Bailey had done his research. 650 firms have the capability. If even half participate, we could produce 500 panels a day within 3 months. The general turned to the Ministry of Supply representative. "I want production started immediately." But there was a problem. Archibald Hamilton, whose bridge design had been rejected in favor of Bailey's, claimed patent infringement. His argument was that Bailey's pin joint system was similar to one he had patented, though Bailey's original 1936 proposal actually predated Hamilton's patent. The legal challenge could delay production for months. Bailey's response was characteristically practical. He gathered the patent documents, his own 1936 proposal, and the complete design specifications for both bridges. Then he invited Hamilton to Christchurch. "Your patent covers a specific pin design," Bailey told Hamilton when they met on May 15th. "I'll modify my pins to avoid any overlap. But more importantly, I want you to see something." Bailey had set up 2 demonstrations. First, a Hamilton bridge, which required specialized equipment and trained crews to assemble. It took 12 hours to build a 60-foot span. Then Bailey's bridge, untrained soldiers, basic tools, 120-foot span in 8 hours. "This isn't about patents or credit," Bailey said. "It's about giving our forces what they need to win. Your bridge is excellent for permanent installation. Mine is for combat. We need both." Hamilton withdrew his objection the next day. He would later receive £4,000 compensation for his earlier bridge designs, while Bailey would eventually be awarded £12,000. Lieutenant General Sir Gifford Lequen Martel would receive £500 for his box girder bridge design that had influenced some aspects of the Bailey Bridge. The first production order went to Braithwaite and Company on July 1, 1941, 1,000 panels, to be delivered by September. Within a week, orders had gone to 50 more firms. Each firm received the same simple specifications, the same basic blueprints that could be understood by any competent engineer. Frederick Marshall, production manager at Rubery Owen, later testified, "We received the Bailey specifications on a Monday. By Wednesday, we had retooled 2 production lines. By Friday, we were producing our first panels. No special equipment needed, no new techniques to learn." Production accelerated rapidly. July 1941, 300 panels. August, 1,200. September, 3,000. By December, when the first Bailey bridges entered service with the Army, production had reached 5,000 panels per month. By 1944, production would peak at 25,000 panels per month across all manufacturers. The first operational Bailey Bridge was built in Tunisia on November 26, 1942. The 237th Field Company, Royal Engineers, needed to bridge the Medjerda River near Medjez El Bab under enemy observation. The existing ford had been destroyed by flooding. Major Kenneth Ray, commanding the bridging operation, had trained on Bailey bridges for exactly 2 days. His men had seen them for the first time that morning. Under sporadic artillery fire, they assembled a 140-foot double-single Bailey in darkness. Ray's after-action report survives. The simplicity of the Bailey system proved itself tonight. Despite enemy shelling, despite working in complete darkness, despite none of my men having built one before, we had a bridge capable of carrying 40-ton tanks operational in 9 hours. The pin system means you can build by feel. The bridge carried the entire 2nd Armoured Division across the Medjerda. Over 3,000 vehicles crossed in 48 hours. When the bridge took direct hits from enemy artillery, damaged panels were simply replaced with spares, the bridge operational again within hours. The first Bailey Bridge built under fire was constructed at Leonfort by members of the 3rd Field Company, Royal Canadian Engineers, marking the beginning of widespread Bailey Bridge deployment that would see over 3,000 built in Italy alone between September 1943 and May 1945. In Italy, the German strategy of destroying every bridge during their retreat created perfect conditions for Bailey's invention to shine. The Volturno River crossing in October 1943 saw 16 Bailey bridges built in 7 days. The longest Italian Bailey bridge across the Sangro River spanned 1,126 feet. Private First Class Anthony Benedetto, later known as Tony Bennett, was among the troops who crossed these bridges. In his memoir he wrote, "The Bailey bridges appeared overnight like magic. We'd go to sleep with an impassable river in front of us and wake up to find a bridge strong enough to carry our tanks." Lieutenant Colonel Henry Newell, chief engineer of the British 8th Army, calculated that Bailey bridges saved an average of 48 hours per river crossing compared to traditional bridging methods. This time savings proved decisive in maintaining offensive momentum. In Burma, conditions were even more challenging. The longest Bailey bridge of the war, across the Chindwin River, spanned 1,154 feet. Built in sections on floating pontoons during the monsoon season, it demonstrated the design's adaptability to extreme conditions. By D-Day, June 6, 1944, stockpiles of Bailey Bridge components were positioned across southern England. Within the first week after D-Day, 40 Bailey bridges had been constructed. By the end of June, that number exceeded 200. Operation Market Garden in September 1944 provided a dramatic test. The Sun Bridge near Eindhoven, destroyed by the Germans just as the 101st Airborne arrived, was replaced overnight. Captain Harold Young's Royal Engineers constructed a 180-foot double-double Bailey in 11 hours, allowing XEX Corps tanks to advance toward Arnhem. The Rhine crossing in March 1945 represented the Bailey Bridge's ultimate achievement. Blackfriars Bridge at Rees, built by the Royal Canadian Engineers, stretched 1,814 feet, including approach ramps, making it the longest Bailey Bridge ever constructed. Despite heavy fog and German artillery, Canadian sappers completed the bridge in just over 2 days. Winston Churchill crossed a Rhine Bailey Bridge on March 25, 1945. Stopping midway, he turned to Montgomery and said, "This bridge is a poem of engineering." From D-Day to VE Day, Allied forces constructed over 2,000 Bailey bridges in northwest Europe. The total length exceeded 40 miles. American forces, after licensing the design in 1943, manufactured over 200,000 tons of Bailey bridging. General Eisenhower's assessment was definitive. There were 3 developments that shortened the war in Europe. Radar allowed us to fight at night and in weather. The heavy bomber allowed us to destroy German industry, and the Bailey Bridge allowed us to advance across Europe at a speed the Germans never anticipated. The cost-effectiveness was extraordinary. A traditional military bridge capable of carrying 40 tons cost approximately £50,000 in 1941. A Bailey Bridge of the same capacity cost £6,000 and could be built in 8 hours instead of several days. Production involved over 650 firms in Britain alone, plus 300 American manufacturers after 1943. Women comprised 40% of the production workforce by 1944. Quality control was remarkable, with rejection rates below 2% despite dispersed production. The human cost savings were significant. Traditional bridge construction under fire resulted in casualty rates approaching 30%. Bailey Bridge construction reduced casualties to less than 5%, saving thousands of engineers' lives. German commanders consistently underestimated Allied bridging capability. General von Vietinghoff, commander in Italy, stated, "We would calculate that destroying a bridge would delay the Allies for a week. They would be across in 2 days. Japanese forces facing Bailey Bridges in Burma reached similar conclusions. A captured Japanese manual from 1944 instructed, "British floating bridges appear overnight. Destroying river crossings no longer ensures delay." By war's end, over 700,000 panels had been manufactured, weighing 500,000 tons. This represented over 200 miles of fixed bridging and 40 miles of floating bridge capability. Donald Bailey remained modest about his achievement. When knighted in 1946, he responded, "I just drew some lines on an envelope." The brave men were those who built the bridges under fire. Field Marshal Montgomery provided the definitive military assessment. Bailey bridging made an immense contribution towards ending World War II. As far as my own operations were concerned, with the 8th Army in Italy and with the 21st Army Group in Northwest Europe, I could never have maintained the speed and tempo of forward movement without large supplies of Bailey bridging. Without the Bailey Bridge, we should not have won the war. The post-war legacy proved enduring. Bailey bridges served in Korea, where UN forces built over 300. The design influenced all subsequent military bridging, with modern systems still using Bailey's modular panel concept. In civilian applications, Bailey bridges provided emergency infrastructure worldwide. The 1975 Tasmania Bridge, spanning 2,585 feet, demonstrated the design's scalability. India's military maintains 4,000 tons of Bailey bridging, using it at altitudes exceeding 15,000 feet during the 1999 Kargil conflict. Donald Bailey continued his work at the Military Engineering Experimental Establishment, becoming its director in 1945. He served as Dean of the Royal Military College of Science at Shrivenham from 1962 to 1966. He died May 5, 1985, in Bournemouth, aged 83. His obituary in the Times stated, "Donald Bailey gave the Allies a tool that shortened the Second World War by months and saved countless lives." Today in Christchurch, where Bailey developed his revolutionary design, a section of original Bailey Bridge panel stands as a memorial. The inscription reads, "To Sir Donald Bailey, whose bridge carried the Allies to victory and continues to serve humanity worldwide." The bridge, dismissed as garden shed engineering, became the most widely used military bridge in history. From Rejection in 1936 to knighthood in 1946, Donald Bailey's story proves that the greatest innovations often come not from complexity but from elegant simplicity. His blueprint, sketched on an envelope during a train journey, shortened a world war and saved countless lives. The Bailey Bridge stands as testament to a profound truth. Sometimes the best solutions are the simplest ones, and sometimes one person working alone after hours, pursuing an idea everyone else has dismissed, can change the course of history. Bailey's bridge didn't just span rivers, it bridged the gap between certain defeat and eventual victory, proving that in war, as in engineering, genius often lies in seeing the obvious solution that everyone else has overlooked.